In this video, I'm going to explain one of the important concept for PU board examination, that is zero order reactions and its half-life from chemical kinetics chapter. Hello guys, this is Komali M. Welcome to my channel. If this video helpful for you, please do like and subscribe my channel. If you have more doubts, drop a comment. I will do video on that topic. Let us see zero order reaction. A reaction is said to be zero order if its rate is independent of the concentration of the reactants. That is, the rate is proportional to the zeroth power of the concentration of the reactants. Suppose if you see a reaction like A is a reactant gets converted into product, then rate is proportional to the concentration of the reactant for zero order A to the power of 0, because the rate is proportional to the zeroth power of the concentration of the reactants. In place of this proportionality, place a constant that is called rate constant into concentration of A to the power of 0. Anything to the power of 0 is 1. Therefore, R is equals to K into 1, that is K. Rate is equals to K. And we can write the rate for zero order reaction is minus d of A by dt. This minus symbol indicates decrease in concentration of the reactants. And D indicates the differential rate equation or instantaneous rate equation, means a decrease of the concentration of the reactants with respect to the time t. So relate these two expressions, rate is equals to K, here rate is equals to minus d of A by dt. Then minus d of A by dt, which is equals to what? K. Just I am exchanging this dt, moving from left hand side to right hand side, minus d of A, which is equals to K into dt. Multiply both the sides with a negative symbol in order to eliminate this minus from this side to this. Minus into minus plus, and here we get minus. Do integration on both the sides. Do integration on both the sides. Here K is constant. No, we cannot do integration for the constant terms. Then we get like this. Integration and differentiation gets cancelled, and concentration of A will be left, and here also integration differentiation gets cancelled. K into T plus, whenever we are doing an integration, we will get a constant that is called integration constant I. In order to calculate the value of the I, we can get from the initial conditions, that is, when reaction is not started, T is equal to 0 and the concentration of the reactants taken as A naught. Substitute these two values in this expression to get the I value. A becomes A naught, which is equal to K into T value is 0 plus I. K into 0 is 0, then I is equal to A naught. Substitute the value of A naught in this expression. Then we get concentration of A is equal to minus K into T plus A naught. This expression is like y is equals to mx plus c straight line equation. Draw the graph between y-axis and x-axis. Here y-axis is concentration of A. Take on y-axis concentration of A, on x-axis T. Then we get intercept, that is concentration of A naught. Straight line this is this, and slope is minus K. This graph indicates that this is the expression, right? A is equal to minus Kt plus A naught. I am writing the same expression like this, A naught minus Kt. which indicates that this graph indicates that the decrease of the concentration of the reactants with respect to time t. That is, so from this we can write KT move towards the left hand side and A move towards the right hand side, then KT is equal to A naught minus A. Then rate constant K is equal to A naught minus A by T. This is the rate constant expression for the zero order reaction. And one more thing, rate is proportional to the concentration of the reactant to the power of 0, which indicates that the rate is independent of the concentration of the reactants. If you plot a graph between the rate of the reaction and concentration, we get a straight line parallel to the concentration of the reactants, which indicates that the rate of the reaction remains constant throughout the course of the reaction. Let us see the half-life period. Half-life period or half-life time. Half-life period is nothing but the time required to reduce the initial concentration of the reactants to half of its initial value. That is called half-life time or half-life period, which is denoted by T half. And how to get that half-life period? See here, T is nothing but T becomes T half, and concentration of A means the concentration becomes a half of its initial concentration, right? Then the final concentration is nothing but A naught by 2. Half-life is nothing but that is the time required to becomes half of its initial concentration. Substitute these two values in the rate expression we got, rate constant expression we got. Then K is equal to A naught and minus A. A value is nothing but what we got here, A naught by 2. A naught by 2 divided by what is left, T. T is nothing but here T half. Then take A naught as common. Then what is left, 1 minus 1 by 2 by T half. 1 minus 1 by 2 is nothing but half. So A naught by 1 by 2 is there, right? 1 by 2 T half. So we can write T half on exchanging. Then we get T half is equal to A naught by 2K. This is the expression for half-life period of zero order reaction. This expression indicates that half-life of a zero order reaction is directly proportional to the concentration of the reactants, that is the initial concentration of the reactants. If you draw a graph, T half is proportional to concentration of A naught by 2K. If you draw a graph between T half and concentration of A naught, we get a line, straight line passing through the horizon, and where slope is equal to half K. Slope is equals to 1 by 2K. Zero order reactions generally takes place in a heterogeneous system and some photochemical reactions. Generally, zero order reactions are very less common. Thermal decomposition of certain gases like ammonia on the catalyst surface, which is a zero order reaction, and enzyme catalyzed reactions also zero order, and we discussed photochemical reactions also zero order reactions. Thanks for watching.